So today we are continuing node voltage method for ECE 1220 at the University of Utah. Last time we did circuits with a single unknown nodal voltage, and now we will work with circuits that may have two unknown nodal voltages. So there's no new techniques, we're just applying them to more complex circuits. So let's review the steps of node voltage method. First, we label our ground, and then we label all our nodes either with known voltages or with an unknown variable, like a VA, VB, VC. And then we label currents through all the resistors with variables. Then we write a KCL equation at each unknown node, and by unknown node, I mean we don't know the voltage there. And then the next step is we replaced the currents with expressions that were V over R, because by Ohm's law, I is V over R. And then finally, we solve the single equation, or in this case, the system of equations, because we may have multiple equations. Let's do an example. Here's a circuit from your textbook, problem 3.8. And so let's choose a ground to start. I would choose at the bottom, but you can choose where you want. Here, this will be tracing through from ground plus 6 volts. And then here's another node. Let me make that neater, 6. We don't know what this node voltage is, so I'll label it VA. Then there's also one other node over here, so I'll label this VB. So all of this is one node, and all of this over here is its own node. Maybe I should do them in different colors. Make it easier to see. So we'll use blue on this node. So this is one node. Okay. So let us write a node voltage equation for each unknown node. And let me throw in a few more currents to make it easier to communicate about that. So I'll throw a current here, I1, throw a current here, I2, current here, I3, current here, I4. Okay, so at unknown node VA, here is the KCL I can write. I1 plus I is out, plus I2 is out, plus 3 amps is out. So everything is going out the way I drew it right now. That's fine. That just means by KCL they almost sum to 0. And one of those actually was negative. And then I can write an equation similarly at unknown nodal voltage VB location. So I'm looking at all the currents flowing into this node here. So I have 3 amps flowing in. I also have 4 amps over here flowing in. Then flowing out, I have I3 and I4. Okay, now I need to go through and replace all the currents with V over R's. So I1, VA minus 6 volts over 2 ohm. So remember, we follow the direction of the arrow. Here's the voltage we started at, and here's the voltage we ended at down here, and we subtract the one the arrow ends at. And then for I, it's VA minus 0 over 8 ohm. And then for I2, it's VA minus 0 over 8 ohm plus the 3 amp stays, all equal to 0. And one of your classmates asked me the other day, wait, this isn't amps, this isn't ohms, what's going on? Good thing to notice that, and I'm glad you're doing some dimensional analysis there. So the thing is that these are all volts. So we have volts over ohms, which gives us amps. So actually each of these are in amps. And then if we multiply the whole thing by like 8 ohm to get rid of the denominator, then that's fine, because these ohms will cancel. And again, by Ohm's law, if we have amps times ohms, I and R, that gives us units of volts, according to Ohm's law. So the units are checking out. Okay, now let's go and replace the currents we don't know down here. at node voltage VB location. So I3, so I'll add these two together, this is 7, excuse me. I3 is VB minus 0 over 8 ohms, and I4 is also from VB to 0, VB minus 0 over 8 ohms. Now, what's really interesting about this problem is we do have two unknown nodal voltages, but notice that this equation only depends on VB, and this equation up here only depends on VA. So that's really interesting. So for this specific circuit, this is not a general situation. It turns out that the way this current source kind of separates the two halves of the circuit, the voltage over here is kind of independent of the voltage over there. The two halves of the circuit are kind of working separately. And so only these resistances are affecting this voltage, and only these resistances are affecting that voltage. And then depending on what the resistances are for each of those, that will change what the voltage is like across this 3 amp current source. So you don't actually have to solve a system of equations here. You actually have two independent single equations to solve. But that won't always be true when we get to our worksheet now.